going to look at your JK flip-flop, your D flip-flop, your SR flip-flop. So before we get into flip-flops, we normally look at latches, right? Remember, I've been touching this so many times now. But latches are basically the building blocks of flip-flops. So the main difference between latches and flip-flops is that your flip-flops will be edge triggered, so you will always have a clock when you are drawing a flip-flop, when using a flip-flop. So let's start first with the latch. So we know that they are basically building blocks of memory, right? Your latches. And then they remember the previous state, and then they make the decision, the next decision based on the previous state. So we can just say that they are building blocks of memory, right? So in short, I'm gonna draw all these circuits, but I will upload this notes on my Unisa again. Just remember, I said this is a new laptop. Let me just try to use a mouse. So this is basically a NOR gate, right? A NOR gate. So here I'm drawing an active high SR latch. So this is an active high SR latch. This is a NOR gate. So I'm going to be quick here because we need to cover all the flip-flops. So this is basically the input R. Input R, and then this is input S. Then this will be your output Q, and then this will be output Q naught, right? Okay. So this is basically an active high. We say this is an active high SR latch. Right? Because the normal working condition for this is active. It's basically when it's low, right? The normal working conditions. So the normal working conditions means when S and R are low, then it's a normal working condition. All right. So what do we mean by that? So let's just draw its truth table quickly. So for its truth table, we're going to have the input S, then we're going to have the input R with the output Q and output Q naught. So with this, we know here our input will be, for example, 0, 0. So now we just need to see what happens when our input is 0, 0. I know we have done it many times, so I will be quick. So let's just see what happens when it's 0, 0. All right. It's size small. Okay. So imagine, so before we can do this, we need to know how a NOR gate, the output of a NOR gate, right? So let's just draw a basic 2-input NOR gate here. So we know in a NOR gate, let's say 0, 0. In an OR gate, say for example, A, B with output X. We know in a NOR gate, when we have 0, 0, the output is, in an OR gate, the output is 0, but in an OR gate, the output will be 1. An OR gate is the inverse of a OR gate. It's an OR gate with an inverter. So the output will be 1 here. Then if it's 0, 1, we know in an OR gate, the output is going to be 1. In this case, the output will be 0. So 1, 0. In an OR gate, the output will be 1. In an OR gate, the output will be 0. And then 1, 1. In an OR gate, the output will be 1, but in an OR gate, because we invert, everything, the output will be 0. But here I'm going to put a 0. Okay, so now we can start. So if we have 0 here, 0 here, and then we have again a 0 here, right? So what's going to happen? So when S and R is 0, so let's check here. Let's start with the normal working condition of this being 0 here. So if Q, for example, is 0, we're going to feed it to this S, right? So here we're going to have a 0 and a 0, right? 0 and a 0, we know it gives us a 1. So our Q naught will be a 1, right? This Q naught is going to be, it's going to move from here and become an input here as a 1. So 0 and a 1. So 0 and a 1 will give us a 0, right? 0 and a 1 will give us a 0. So a 0 is here, 0 comes here, 0, 0 gives us a 1. We take this one here, 0, 1. It gives us a 0, 1. It gives us a 0, right? Yeah, 0, 1 gives us a 0. So in this case, we got for this 0, 0, we basically just got 0, 1. Our Q was 0 here, for example, and then it was 1 here. But remember, it's because the memory said 0, said Q was 0. We had to use this Q as 0, right? But it's fine. It's not a problem. Let's continue. Let's continue from here. Let me just erase this. So in this case, now we want to test 0, 1, right? 0, 1. 0, 1. So 0, 1, we basically mean we want our S to be 0. And then we want the R to be 1. So then on top of that, we have this. Our output Q was 0, and then Q naught was 1, right? So if we bring this 0 here, we have 0, 0. 0, 0 gives us a 1. If we take this one here, we have 1, 1. 1, 1 gives us a 0. You see 0, 1. So now it means it stays like this, right? This becomes a 0, and then this becomes a 1. So the output will remain like this. If you put this one here, you're going to have 1, 1. The output will be 0. This 0, you bring it here, you're going to have 0, 0. The output will be 1. So the circuit will remain like this. So you can see that there's no change. If it comes from 0, 0, there's no change, right? Now, let's change to 1, 0. 1, 0. Our input is basically 1, 0. So let's change this. Our SNR are changing. So this is going to be a 1 for S, and then for R is going to be a 0. So 0, you bring it here, you have 0, 1. 0, 1 gives you a 0. So this is a 0. 0, this 0, you bring it here, 0, 0 gives you a 1. So this changes and turns into a 1, right? This one, you bring it here, 1, 1. 1, 1 gives you a 0. 0, 0, 0, 0 gives you a 1. So this is Q becomes 1, and then Q naught becomes 0, right? So this is going to be a 1, and then this is going to be a 0. So in this case, we call it a, this one we call it a reset, and this one we call it a set. How do we see that? Reset, because set is 0, so it's called a reset. Here set is 1, it's called a set, right? So let's just put this comment. So normally when you do that, when you draw the truth table, you will, when they give you this, most of the time they want you to draw the truth table. So you need to mention, you need to put this comment as well, right? So now we already know two cases. We know this case is reset, reset, and then we know this case is set. All right. Then continuing, we need 1, 0 now. We have 1, 0. We need 1, 1. Before 1, 1, remember memory, if memory serves us right, we started with 0 here as Q. Let's go back to 0, 0 here and see what happens, right? So let's go back to 0, 0, 0, 0. So now 0, 0. Sorry. So 0, 0 as our inputs. This will be 0 and this will be 0. So we're going to take this one and bring it as an input here. 0, 1 will give us an output of 0, right? Then we take this 0 here. 0, 0 will give us an output of 1. So it means it doesn't change. Do you see that 0, 0 means no change, right? The circuit stays in its previous state. 0, 0 means no change. Now we have 1, 0. Sorry, guys. So here, because of this previous state, that's why I was saying it remembers it remembers the last state. It makes its decision based on the last state. That's your latches and flip-flops, right? So the last state was 1, 0 here. It was like this. So the output remains the same because both these inputs are off, right? They are 0, 0. It remains the same. So we can say for 0, 0, it means no change, right? So you can just do it like this, no change, no change. No change. No change, right? So now, then after this, we have one more combination. So I just wanted to show you guys here what it means. So it means here you can just do XX and then write no change. You can delete this. Let's do it like that so that you just follow the same standard for this truth table, right? So here I can put an X, I can put an X, and then I can just say no change. Basically, the output will not change. It will be the same as it was in the previous state, right? So now let's have 1, 1, 1, 1. So now if we have 1, 1, let's have 1, 1 in this previous state and see what happens. Then we'll have 1 in there. We'll swap this around and see what happens even when we switch the ones around, right? So 1, 1, 1 and a 1, 1 and a 1. We're gonna bring this one here. So we're gonna have 1 and a 1. It's gonna give us a 0. 0 comes here, right? 0 comes here. 1 and a 0. 1 and a 0 gives us a 0 now. 0. We take this 0, we bring it here. 1 and 0. 1 and 0 gives us a 0. Here's the 0. 1 and 0. 1 and 0 gives us a 0. So here we have 0, 0. Remember, this is a latch. It should be on and off. So this condition, we say it's invalid, right? Invalid. You can't have both yes and no at the same time, right? Invalid. So the light can be green and red at the same time. Invalid. So that's why we will call this invalid. So let's check again. We checked with this when it was 1 and 0, right? So let's check if it's 0 and 1. What's going to happen? This is 0 and this is 1. So this 0 here, 0 and 1, 0 and 1 is going to give us a 0. So the 0 is here, right? Is this 0? We bring it here, 0 and 1 is going to give us a 0. We take this 0, we bring it here. 0 and 1, we know it's going to give us a 0. 0 and 1 is going to give us a 0. This 0 here, again, 0 and 1 is going to give us a 0. Even if you say 1 and 0, for example, 1 and 0, it will give us a 0. So it will still be like this. No matter the previous state, it will still be invalid. So this is basically your SR latch. SR latch. The most important thing, remember, it's a active high SR latch, right? And the normal working conditions are low, right? You see, like here it is. When the inputs are low, what happened? When SNR is low here, when SNR is low, there's no change. It's a normal working condition. But when it's high, when it's 1, it's invalid, right? So remember this words. This is an active high SR latch, right? So I'm gonna draw an active low SR latch quickly, but I'm not gonna explain it. Well, for the sake of time, but I have explained it more than 3 times already now. Okay, so let's use black. So this next latch is basically an active low SR latch, right? Active low SR latch, and it's made out of NAND gates. This one was made out of NOR gates. This one is made out of NAND gates. Okay, I know here. I know here. And I want you guys to focus on something as well here. There's gonna be a difference in our output, in our inputs, I mean. So this will be Q, and then this will be Q naught. Q naught. Check, this is S, and then this is R. But with the active high one, this was R and S. The top one was R, the bottom one was S. So this is S and R. So this we say we're going to call it an active low. You see active low SR latch. Normal working conditions. So normal working conditions is when both inputs are high, right? All right, let's see if we are right. Quickly, let's just see if we are right. Here. So normal working condition is when they are high. So if it's 0, 0, it's gonna, if we say 0, 0 here, it's gonna give us invalid. So let's just start with 1, 1, for example, right? 1. So this will be S. Let's go for the color green. Just want you guys to have a view of this as well, so that you can see the difference. Yep, I think this is better here. All right, this will be our S, this will be our R, Q, Q naught, and then the comment. With that, this will be our 0. It's fine, but we're not gonna start with 0, 0, right? 0, 0. This will be our 0, 1. This will be our 1, 0, and then this will be our 1, 1. So let's start with this. So let's start with our inputs being 1, 1. Let's see if this is a 1 and then this is a 1. Let's say here this was a 1 here, right? It's fine. So 1, we're gonna bring a 1 here. No, we need to draw the truth table for the NAND gate first so that it becomes easier for you guys. A, B, X. So the truth table for a 2-input NAND gate, 0, 0. So in an AND gate, when both inputs are low, if both inputs are low, the output will be low, right? In an AND gate, it will be high. 0, 1. If it's like this, it will still be low, but in an AND gate, it will be high, right? 1, 0. It will be low, but in an AND gate, it will be high. 1, 1. 1, 1. It will be 0. In an AND gate, it will be 1, but in an AND gate, it will be 0. So now if we have 1, 1, we know the output is 0. So we're gonna have a 0 here. We're gonna bring this 0 here. 1 0 1 0. The output is 1. Here's 1. We bring this one here. 1 1 1 1. Right? The output is 0 1 1. The output is 0. So it means nothing changed. You see. So this was already a 1 here. This becomes 1 0. So let's put 1 0 for 1 1. 1 0 1 0, but we don't know yet if anything changed, right? So let's use this history and then go to 0 1 here. So we're just gonna keep the history as it is. Then here we're going to go for 0, then we're gonna go for 1, right? This should be a reset, right? Reset. For example, this S must be 0, the Q must be 0, and then this must be reset. Then Q naught must be 1, right? Let's see if we are correct. Okay, so we take this one, we bring it here. We have 1 1 1 1. The output becomes 0. We take this 0, we bring it here. 0 0, the output is 1, right? So we bring the 1 here, 1 1 0. So it has reached its final state. So we know that this was 0 1. For 0 1, Q is 1 and Q naught is 0. So let's do this. Sorry. Okay, let's see. 0 1. So we had Q1, and then we had Q naught 0. Can I please complement this here? Q naught 0 complement. Yeah, okay. So this is reset. Yes. Yeah, I was correct. Reset. Right, because this is 1, right? Yes, this 1. Okay. No. Okay, let's look at this one properly. Let's go again. 0 1 1 1. The output here is 0. We bring 0 here. 0 0 0 0 0. It's a 1. Okay. Our Q is 1. It's fine. And then our Q naught is 0. Okay. Let's continue. Let's make all the cases first. All right. So let's look for your S being 1 and your R being 0. S being 1, R being 0. So this is a 1, and then this is a 0 here, right? So this Q, we're going to bring it here. So we're going to have a 0 and a 1, 0 and a 1. Then the value 0 and a 1, the output will be 1, right? The output will be 1 here, 0, 1. Yeah, the output will be 1. Then we bring this one here, 1 1. The output is 0. So here the output will be 0 0. Then this 0 is gonna come down here. So 0 0 0 0, the output is 1. Then 1 1, the output is 0. So it has reached its final state. So we see that our Q, for example here, our Q becomes 0 and our Q naught becomes, what is our Q naught? Our Q naught becomes 1. Let me change this. 0, Q naught becomes 1. Maybe it's okay, yeah, it's correct. Sorry, yeah. All right. So now we have the case that we haven't covered. It's 0 0. And then I think we covered 1 1 based on the history of 1 0, right? So let's cover 1 1 based on this history of 0 1 to show that it's a no change. 1 1, it's no change. So let's cover that quickly. All right. So we say we want to cover 1 1. 1 1, we should have 0 1 as an output, right? We should have 0 1. So let's see if it's correct. So we're going to bring this 0 here. 1 0 should give us an output of 1. This one, we bring it here. 1, 1 should give us an output of 0. 0, we bring it here. 1, 0. It's going to give us 1. So it means this doesn't change, right? So it means with 1, 1, we still got 1, 0, 0, 1 as well. 0, 1. 1, 1, we got 0, 1, right? So it means with 1, 1, there's no change. Do you see that? It doesn't change. If this light before we change the inputs, if this light was off and this one was on, for example, let's say the green one was off, then the red one was on. Even when we change this input to 1, 1, right, it will still remain the same. So that's why we say no change. So for this, I'm just gonna put don't cares, double X's here. Call them don't cares. You don't care. Ugh. Okay, let's see. Okay, let me just do it like this. So here X and then X, and then we can say no change here. No change. Okay. Before with that being said, let's change this to 0, 0, 0, 0. For this, we should get invalid. Remember here, there's an active low. The normal working condition is when both inputs are high. This is normal working condition. So here, this should be invalid, right? But let's see if we are correct. 0, 0. Let's work with this previous state. We're going to take this 0 here. So here we're going to have both 0, 0, 0. The output will be 1. We bring this one here. 0, 1. The output is 1, right? We bring this one. We bring it here. Put the one here. 1, 0. 1, 0. The output is 1. We bring this one here. 1, 0. The output is 1. 0, 1 and 1, 0. They yield the same. So this one is going to come here. So now you see that both inputs are high, right? So you have 1 and then you have 1. Then this makes you reach an invalid state again. So we can say this is right. So this will be invalid, guys. Invalid again. Invalid, right? Because both the inputs are high, so they can't be high. So here both the outputs are high. Here both the outputs were low, so that's why it was invalid. So this is the difference between, okay, sorry, and then this will be your set, and then this will be your reset. Set, you will see it with the Q being 1, the output Q being 1, and then this will, you will see it with this being low. So it's basically the opposite of this first one, right? Basically just the opposite. So the output Q is 1 here, and then here the output Q is 1 here. So just make sure that when you read the question, if they're asking for active high, know that you're going to use NOR gates. If they're asking for active low, know that you're going to use NAND gates. The most important thing here is this. The explanation you will see now when we do the flip-flops, it's this. You need to know how to draw this, right? Then you just need to know this truth table, right? Only this and this. Basically this and this. Then you are done with your lectures. To explain, guys, you don't need to stress yourself. Read this truth table. You can just say that if both inputs are low, there's no change. If, what is it? If R is set, for example, R is set, the circuit is in reset state. In whichever state, then you will explain this one. Then here, If both are high, it's in an invalid state, right? Deeper, yes, this is a race condition, right? It rushes to be off. So you don't really know if it's off or on, but it's literally off. It's just that that light will flicker a bit if you do the practical, but if you do it using these gates, you just need two NOR gates. Actually, one NOR gate, that IC, that small black IC, just need one. Then from there, you can just create your own two inputs and then your own output. But let's say, for the sake of this topic, two NOR gates, then you do that. You make your two LEDs right here for your outputs. Then here you plug it to 5 volts. You will see that it's off, but it flickers just a little bit. It's not stable. Even here, it's not stable once, right? It's not on. Just flickers a bit. It's like when there's load shedding, or when there's about to be load shedding, or when you're using the generator and the petrol is about to finish, something like that. Okay, with that being said, the most important thing from here is our flip-flops, right? Flip-flops. So with our flip-flops, we are going to start first with the SR flip-flop, right? The SR flip-flop. So the flip-flops were meant to erase these conditions, for example, these conditions, these invalid states that we have here. And then the flip-flops, at least we know that the biggest difference is that they use a clock pulse, right? So which one can we draw? Let's draw this one with the 4 NAND gates. So it means with the NAND gates, we are using this one, right? With me, we are definitely using this one. Or let's use the NOR gate. Let's use this one that we started with, just to show you that where it's coming from. So we're going to draw an SR flip-flop based on the active high SR latch, right? So it's basically this SR latch the way it is. It's basically this SR latch. Then we just put two AND gates there, but let's do it quickly. NOR gate. NOR gate. So it's now we're just drawing the SR latch first. So we know this is normally our Q, and then this is normally our Q naught, right? Q naught. Then we know this was gonna be our R, this was gonna be our S. Right? So now we need to add an AND gate here. AND gate. Here, an AND gate, right? Then we will have our input. Then we're going to have a clock pulse. Remember, with flip-flops, we have a clock pulse, right? Clock. So this, remember, this was R and this was S. So this becomes our R and this becomes our S. So basically here, in your truth table, so you need to know how to draw this, right? And then in your truth table, this will be S, R, this will be Q, Q naught, then it will be comment. Then you can say 0, 0, 0, 0 will be a don't care case. Don't care. Which one is it? This one. The don't care case. So it means no change. There's definitely no change. X, no change. So it means when both these inputs are low, right? There will be no change on the previous state. Like the circuit will be in its previous state. That's what this means. So now when S is low and R is high, this will be, the Q will be off and the Q naught will be on. We call this state the reset. Just do this. Okay. And then from here, we know if it's 1 and 0, Q will be 1, and then Q naught will be 0. This we call the set. Yeah, set state. Set because Q, yes, Q is high, right? Then we know that with the 1 and a 1, right, it's going to give us both highs. So this is invalid, right? This is invalid. It's basically, we are basically just here. So it means this SR flip-flop didn't get rid of this case for us, right? So now we needed something that can get rid of this case. So you need to know, remember, you need to know this, and you need to know this. From this, you just need to know how to draw this and the truth table. From the truth table, you can explain it. When both inputs are low, there's no change on the output. There's no output. There's no change. Then like this, it's a reset. Like this, it's a set. You will see when we explain the JK flip-flop just now. Maybe we can use some of the words from the then 1, it's invalid. You see, because this can both be high. This is a set and a reset latch. Remember, this is still a latch here, coupled with this 2 AND gates. All right. So this is the SR. SR flip-flop. Okay, now let's jump quickly to the JK flip-flop, right? JK flip-flop, right? So the JK flip-flop will have both two inputs called J and K, right? So now for this, let's use this one. So we're going to use this active low SR latch to draw the JK flip-flop. Active low SR latch, we know that it uses this. It uses NAND gates. NAND gates. Then we know, for example, this is Q naught. Then we need to couple it with something. So we're going to couple it with NAND gates. This one we couple with NAND. Here again, NAND. Then we're going to take this. So this will have 3 inputs now because of the clock, right? We're going to take this. Then we have our K. So this is our clock, the one in the middle. This is our clock. And then this will be our J. And then this will be our K. So we need to take this input here, bring it all the way down here, right? And then similarly, this one here, we're going to bring it to conduct here. So let's do that. Let me just extend this. So this one, we know it comes here. And then this one will come all the way to here. So this is basically our JK flip-flop, right? So let's do the truth table quickly. So we're going to have our clock. pass, dot pass. So dot pass, and then let's have a J, let's have a K. Do we need S and R? Okay, let's just have an S and R. S and R. Let's have a Q, have a Q naught. Let's have our comment. Comment, right? So when the clock pulse is 0, okay, that is, you need a, what is this again? You need a 2-input AND gate. Let's talk about the AND gate. So AND gate, A, B with an X. If this is 0 and 0 in an AND gate, the output will be 0, but in a NAND gate, the output will be 1. If this is 0, 1, AND gate, it will be 0, NAND, it will be 1. 1, 0, AND gate, it will be 0, NAND gate, it will be 1. Then 0, 0, it will be 1, right? It will be, sorry, 0, 0 will be 0. Wacht net 'n bietjie. And 0, 0 will be 0. NAND is a 1. 0, 0, 1. Oh, not 0, 0. This is 1, 1. Sorry. 1, 1. It will be 1. Then NAND, it will be 0. So now we know that here, for us to get an output of 0, right? To get an output of 1, for example, let's say, yeah, 1, 1, 2, 3. To get an output of 1 of these inputs must just be low, right? It's 3 inputs. So if the clock signal is already low, there's a 3-input AND gate. If it has a 0 already, it means my output is an AND gate. My output will be a 1, right? The output will be a 1, right? So we already know that's one thing that I wanted to remind you guys when you need to explain it like that. So this, when the clock is low, right, we don't care what the value of J and K is. Let me do it like this. We don't care. J and K, we don't care, right? We know that the value of S, for example, will be 1. Let's go here. The value of S will be 1. The value of S will be 1. S is this value. Remember, it's 0 here. So you see, the value of S will be 1. Remember, this was your, it was this one, the one of the NAND gate. It was this one, right? The value of S will be 1 and the value of R will be 1, right? It will be 1, 1. You will be in this case, right? Look at this. With just 1, 1, 0, the clock. So this will be 1, 1. Why are we saying that? Because in an AND gate, the output will be 0, but in a NAND gate, the output will be 1. So we know this will be 1, and then this will be 1. It takes us back to that condition of this gate. Where is it now? This gate. When it's 1, 1, there was no change, right? So let me finish. So this will be S, and then this will be S will be 1 and R will be 1, right? Then this will use basically the previous state, So in this case, let's just say 0, 0, 0, 1, for example. But it depends on what we set Q to when we're doing this, right? So, but in short, there will be no change. No change. If we're going to do it again, and then we start with Q being 1, right? You will see that here it will be 1, 0, right? Output will be 1, 0. It goes back to this. Where is it? It goes back to this, right? 1, 1, we decided no change because we had two conditions. Remember, we had the other one, then I decided to cancel this out. We had 1, 1 when it was 1, 0. This one was 0, 1, for example. Then we had 1, 1 from this where it was 1, 0. Right? Then we said we're going to say it means no change. Then now if you have a clock signal of 1, right? If you have a 1, then your J, for example, is 0, 0, right? Your S becomes 1, your R becomes 1. But the most important thing here is that this becomes a 0, 1. Né? This becomes a 0, 1. Why does it become a 0, 1? Your S and R is 1, 1. Do you see that these latches were the building blocks? Keep skipping that. You see 1, 1. The moment you remember, a flip-flop is basically still your SR latch, right? The moment this is 1, 1, there's going to be no change. So we don't even need to go further, right? 1, 1. This must change. This must change first for something to happen. No change. Yep. Now let's see if we have J1, K0, the S becomes 0, the R becomes 1. Then we know that, the Q becomes 1, the Q becomes 1, and this becomes 0, right? Then this, we call it set. Set Y, Q is equals to 1, right? Set. So it was 1, 0, 0, 1 here, 0, 1, 0, 1. Let's look for S and R being 0, 1, 0, 1. We had 1, 0, so we had this condition. Set because Q is 1, right? And Q naught is 0. So we call that a set. Set. So your circuit is in a set state, right? Then the clock pulse being high again, if you have a 0, 0, 1, this is going to be, your S is going to be a 1, then this is going to be 0. We know if it's like this, 1, 0, for example, this becomes 0, 1, it's just the inverse of this, right? 0, 1, and this Q naught, we say this is reset because Q naught is equals to 1, right? Q naught is equals to 1. So look at this properly. I'm gonna show you now. Let me do it. Let me finish, then I'm gonna show you the trick. 0, 1, and then let's go to 1, 1. So if we have 1, that being on, and then we have 1, 1. So this is the purpose of the JK flip-flops, right? Remember now, remember that if we had the input 1, 1, what was happening? Let's go back and see. 1, 1, there was no change, okay? 0, 0, we had invalid, okay? Great stuff. So now, if we have 1, 1, then the value of J and K is basically 1, 1, then our S here, depending on the state that it was in first, right? It becomes 1 and 0, right? 1 and 0. I want you guys to focus here. Remember for invalid, here the normal working condition for this circuit was when S and R were high, right? But for 0, 0, so now it eliminates that 0, 0. Do you see you don't get the 0, 0 anymore? It eliminates this 0, 0, which is invalid. Instead of 0, 0 being invalid and that race condition that I was talking about, it gives you the two options of 0, 1 and 1, 0, right? That's what the JK flip-flop does. It eliminates this invalid state that you had, right? That you had here, then it toggles that state. So this and this will switch, and when it switches, this output will switch as well. So it means the light will be on, off, or red, like the police van, for example, or the emergency lights. Let's say it had two lights, right? Yellow and red. So it will be yellow, red, yellow, red, yellow, red, yellow, red, yellow, red, toggling, right? At every clock pass. So this becomes one. If this is 1 0, for example, 1 0, then this will be 0 1. 1 0, it's this one. 1 0, so it will be 0 1, 0 1, right? Then again, with this, if we have 1 here, remember I said it toggles. So with this, for example, with this combination like this, we still gonna get this. We're gonna get this as well. We're gonna get a case where our S becomes 0, and then here it becomes 1. Then our Q will be 1, and then our Q naught will be 0. So to explain this case together, right, we say toggle. Toggle. So to represent it, you can represent it like this if you want, but you can also use, for example, X here, X. Are you with me? Or maybe just X and X here. Do you get my point? Because now we don't care if this is, no, but here we care. This must be 1 0. It mustn't be 1 1. Okay, so you can use the X here and X here now for this one. But you can draw it like this, just for the sake of your topic. You can just draw it like this, just to explain that this is toggle. So if you need to explain it, the most important thing here is to learn the truth table. This, from here, from this line, from 1, 2, 3, 4, right? 4, 1, 2, 3, 4. It's the same as this. It's the same as this. You see? 1, 2, 3, 4. Everything is the same, right? The only difference here, it's this one. When J and K was 1, 1, right? We had two possibilities. Now we had a 1 and a 0, and a 0 and a 1. And the output of a 1 and a 0, we know from this. From this, 1 and a 0 gives us a 0 1, right? And then we know 0 and a 1 gives us a 1 0, right? You guys with me? So we call this toggle. So you will explain by saying that if the clock is slow, there's no change, right? If the clock is slow, there's no change. Definitely. There's no change in the output. The circuit will be in its previous state or previous memory, right? Then if, for example, J and K are low, there's still no change, right? There's no change. The circuit will be in its previous state. Then you can say if J is 1, for example, yeah, if J is 1, Q will be 1, right? You see, Q will be 1. And then if K is 1, Q naught will be 1. Are you guys with me? And then if both inputs are high, J and K is high, the circuit will be in a toggle state. It will toggle, right? Okay, so just for theoretical stuff, we can say a JK flip-flop, you can see a JK flip-flop is basically an improvement of the SR flip-flop, right? Where, so it's basically an improvement of, guess I will upload this note, of SR flip-flop, where S is equals to R is equals to 1. Remember, we had this problem when S and S, when this is R, when S and R is equals to 1. This is the problem that we had here, the invalid one, okay? Let's see from our thingy. Yeah, where S and R is equals to 1. But for the, you must check. You see this explanation? It's actually for the active high one. Active high one. So with the active low one, the problem is this, when they are both low, when S and R is equals to 0. So for the sake of this one, let's say S and R, for example, is equals to 0 here. But now, if you were drawing this one, if you were drawing the one using this, the JK flip-flop using this, right? You will say when SNR is equals to 1, right? So remember the difference between the active low and the active high, right? But it fixes this problem. My point is it fixes this problem, right? And now again, basically, if J and K are both high at the clock edge, like if your J and K are both high, right? The output will toggle from one stable state to another. It is so it will toggle. So you see, this is very important to say. If they are both high, then it will toggle. So now in this way, it means that it will be on, for example, then it will be off. It will be on, it will be off. Then if J and K are different, then the output Q takes the value of J at the clock edge. So this is what I explained here. If J and K are different, right? It takes the value of J, right? Look at this. Here, 1, it took 1. J and K are different. It took Q is 1. This is our output. Here, J was 0. Q is 0, right? It just takes that. So this is basically your JK flip-flop. Quickly, I'm not going to be long. Let's just do the D flip-flop. Remember I said one day they asked about the D flip-flop. But the most important thing here, you need to just know this truth table. So here you can just say toggle. So this is the same as your latches. It comes from your latches, right? It comes from this truth table of the latches. Then it just has two inputs, JK and the clock. But everything else is the same. So for the D flip-flop, the last one, D flip-flop, it's called the delay flip-flop. So this one is normally used for counters and shift registers. Counters, I basically to count like to count down, and you can use a D flip-flop for that, right? Your shift registers, remember what we did with the shift registers, but yeah, you also do them in this module. You can use it for shift registers as well. So, but let's draw it first and then we'll see from the truth table how it works. So let's draw it with the NAND gates. So these are NAND gates, but we know now we are drawing the latch for the 5th time, right? So this is basically our latch. Our SR latch. So here we know this is a Q, and then this is a Q naught. Then we know that normally this was just an S and an R, right? So now we know we're going to couple this to an AND gate here. NAND gate, I mean NAND, and here NAND. Then from this NAND, this is a 2-input NAND. Let's do here as well, 2-input. So here, this one, this input, we're going to couple it to this input, right? Then this input, we're going to put an inverter here. Inverter, let me make the circle a bit bigger. Inverter. Then it's going to become an input to this, right? So this is basically, let's see, I hope it doesn't delete everything. This is basically an AND gate. Yeah, NAND gate. So here we will have our T, and then we will have our clock, right? D and clock. So this is basically our D flip-flop. Sure. So let's do the truth table quickly. So you will have, your input will be a D. It will be, I'm not going to put S and R for the sake of time now. It will be D, then it will be clock, right? Then here you will have your Q, and then your Q naught. So now, because you only have two inputs, so there's four possibilities, right? It's both D00, right? 00. Now, if it's 00, your Q, for example, the output will be 0. And then Q naught, the output will be 1, right? For the second time, if D is 0 and the clock is on its edge, on its rising edge, right? So this will be 0, 1. Your Q will still be 0, 1, right? Okay. Then when you have your D to be 1, your D, if your D is 1, then your clock is low. Do you see that it jumps back to 0, 1, 0, 1, right? So this D flip-flop is basically just getting rid of 1, 1, and 0, 0. Do you see that? So here, if you have 1 and a 1, your Q becomes 1 and Q naught becomes 0, right? Do you see in this case, you have never hit a case whereby you have 0, 0 or 1, 1, right? So what we can say, what we can also see, this is basically the most important thing here. The most important thing here is that the change of the state of the output is dependent on the rising edge of the clock, right? In this clock, it needs to be on the rising edge for the state to even change, right? If the clock is not on the rising edge, if were to do it like going bit by bit, you will see that if this is not on a rising edge, if the clock is not 1, if the clock is not rising, if it's not on, the output will not change. Have you guys with me? So that is how it is helping us not to reach this invalid and toggle state. So let's, okay, we are basically done, but now let's just summarize everything, right? So we had the active high SR latch, right? We said it's active high because the normal working condition is when S and R are low. Here, S and R are low. Then there was no change, right? Then 1 and 1 was invalid. So this latch is the one that makes us, this condition is the one that makes us, that made us wanna develop flip-flops, right? This is the reason for flip-flops. Then again, we had this condition where 1, 1, this is the active low. 1 means no change, and then 0 was invalid, right? So now this condition made us introduce the SNR flip-flop. Then we saw the SNR flip-flop is just useless. It's the same as that one. It still has an invalid condition. It's just that it uses a clock. So the difference between the latch and this is the clock signal, right? Then we saw that we still reach this invalid condition. Then we introduced the JK flip-flop to get rid of the invalid condition, right? Then we introduced that, and then we saw that both J and K being high, this 1, J and K being high, it produces this toggle state where the circuit is switching between 1 and 0, 1, 0, like red, green, red, green, red, green, as if it's an emergency vehicle, right? Then we said, okay, let's try to see what we can do to eliminate this. Then we designed the D flip-flop, right? Then the D flip-flop, we said the D flip-flop is controlled by the clock signal. It only has 2 inputs. So if the clock is on a rising edge, right, the output is dependent on this. So the output will only change when the clock is on the rising edge. So that's our flip-flops, guys. We are done with flip-flops. The one that we didn't cover is T flip-flops, but they've never asked for the T flip-flop. So, but I don't want to say don't study it. I'm sorry for mentioning it, but yeah, it's T flip-flop. But they've never asked it before. Yeah, so just know this flip-flop, know your JK flip-flop, then we can know these things. Then everything else I will definitely upload for you guys on my Unisa. Any questions?